Hello friends, I welcome you in lecture number 24 on group theory. In previous lecture we have defined normal subgroup, and in this lecture also we will discuss normal subgroup. So if we recall that suppose H is a subgroup of a group G, then H is called normal subgroup of group G if A inverse HA belongs to H for any element of group G, for any A belongs to G and for any H belongs to subgroup H. If this condition is satisfied, then we say that H is a normal subgroup of group G. Now the question is whether every group has a normal subgroup or not. Suppose G is a group under binary operation star, then whether there exists a normal subgroup in a group G or not. So answer is yes. For any group there are always at least two normal subgroups, and those two normal subgroups are trivial subgroups of group G. We have discussed about trivial subgroups. Every group G has two trivial subgroups. One is set containing identity element of G. This is always a subgroup of group G, and another trivial subgroup is group itself. So these two are trivial subgroups of group G. Here E is the identity element of G, and these two will always be normal subgroup because this condition will be satisfied. A inverse HA belongs to G. For example, if we consider this subgroup containing identity element of G, and if we want to check whether this is a normal subgroup or not, then we have to check that for any element A of a group G and for any element H in capital H, we have to show that A inverse HA is an element of capital H. Now here capital H is the set having only one element, identity element. So I have to check for only one element. So I take H equal to E, A inverse E times A. Now because E is the identity element, E into A will be equal to A by the definition of identity. And by the definition of inverse, this is equal to E, and this is in this set, which is our subgroup. So this condition is satisfied for every element of group G and for one element of this subgroup H. Therefore this is a normal subgroup of a group G. Similarly, if we consider group G itself, another normal subgroup of group G is group itself. Then if we take H equal to group G itself, then this condition will be automatically satisfied because A is an element of G, H is an element of subgroup, but H we have taken as G itself. So this condition will be automatically satisfied. So every group has at least two normal subgroups. One is subgroup containing identity element only, and another is group itself. So these two are known as trivial normal subgroups. So I have written here, let G with star be a group. We know that G always has at least two subgroups, set containing identity of G and group itself. These two subgroups are known as trivial subgroups, and trivial subgroups are always normal. So they can ask you to write down the definition of normal subgroup, and they can ask you give an example of normal subgroup. Then you can simply write these two as example of normal subgroups. These are trivial normal subgroups in any group G. We consider another example. Consider the group G of 2 by 2 matrices with rational entries and non-zero determinant. let capital H be the subset of G consisting of matrices whose upper right entry is 0, that is matrices in this form A0 C D. This upper right entry is 0, and we have to check whether H is a normal subgroup of group G or not. So first we write down description of group G. Group G is given as set of 2 by 2 matrices with rational entries and non-zero determinant. So that is, we have this type of matrices. Suppose capital A is the notation for matrix of order 2. Here we write A, B, C, D, and condition is A, B, C, D are rational numbers. That means they are in the set of rational numbers Q. And another condition is determinant of A is non-zero. G is the group of 2 by 2 matrices with rational entries and non-zero determinant. And H is the subset of G with this type of elements. This entry is 0. So we write down H equal to, we have to collect this type of elements A, 0, C, D. From this group G, we have to collect elements whose upper right entry is 0. And here question is whether this H is a normal subgroup or not. So to check whether H is a normal subgroup, we have to, suppose we want to prove that H is a normal subgroup, then we have to show that for any matrix in group G and for any other matrix, say D, in subgroup H, we have to show that A inverse into D into A inverse H into A. Instead of small a, our condition is A inverse H, A belongs to H. Instead of small a, we have matrix A, so we write A inverse into A. Instead of small h, we have matrix D. So we have to show that this matrix is a member of this H. So we are taking capital A in group G. So that means this upper right entry may be 0 or non-zero. And we are taking this element D in subgroup H. And we are multiplying A inverse D and A. So we have to think whether this is possible for every element of group G and for every element of subgroup H. So if we observe, then it seems that this might not be possible. So what we can do is, instead of directly proving this, we can try for particular matrices. We can take one matrix from group G and another matrix from subgroup H, and we can check whether this condition is satisfied or not. So from trial and error we can have the idea, but from this structure we may have intuition that this might be wrong. This might not be true for every matrix capital A and every matrix capital D. So we can try by taking particular elements. So I take one matrix in capital G and another matrix in capital H, that is subgroup. Suppose I take A equal to, here I fix these two entries as 1, 1, and I consider 2 and 3, and I have to take care that these two conditions are satisfied. A, B, C, D are rational numbers and determinant of A is non-zero. Here determinant is 3 minus 2, that is 1, and entries are rational. Determinant of A is 3 minus 2, which is 1, and entries are rational number. So this is non-zero, and therefore A is an element of group G. And we consider element in this subgroup H, so that I consider as Suppose I take h equal to, I consider all the entries as 1 and here I put 0. And I cannot use capital H, I have to use some another notation, say D. H is used for subgroup. So here also we can see upper right entry is 0 and determinant of D is 1 minus 0, that is 1, which is non-zero. So D is in subgroup H because upper right entry is 0 and determinant is non-zero, so it is element from G with this entry as 0. Now we have to check whether A inverse D into A is going to be a member of this H or not. So for that I will require inverse of this matrix A, which is 2 by 2 matrix. And if you recall, we have ready-made formula for the inverse of 2 by 2 matrix. Suppose I have A equal to A, B, C, D, then A inverse can be obtained by this formula, 1 divided by determinant of A, and here we have to interchange these two entries A and D. So D, A, interchange A and D, and you have to make signs of B and C as negative. So instead of B I will write minus B, instead of C I will write minus C. So here we interchange and here we change the sign. So using this formula we can directly write down the inverse of A. Determinant of A is 1 and we write one more step, 1 over determinant of A. We change these two entries 1 and 3, that is 3 and 1, and we make these two negative, so that is minus 2 and minus 1, and determinant of A is 1, therefore this is going to be 3 minus 2 minus 1 and 1. Now I find out that product A inverse D into A. So in the next step I will see that what will be the product of these three matrices. So first I write inverse of A, which is 3 minus 2 minus 1 1, 3 minus 2 minus 1 1. D is 1 0 1 1, and what is matrix A? Matrix A is 1 2 1 3. 1 2 1 3. Now first we multiply these two matrices. We know how to multiply two matrices, first row into first column, first row into second column, and so on. So I first take multiplication of 1 0, that is first row with first column. So 1 into 1, okay, 1 into 1, that is 1, plus 0 into 1, that is 0. Then we consider first row multiplied with second column. So 1 into 2, that is 2, plus 0 into 3, that is 0. Same process we repeat for second row. Second row we multiply with first column, 1 into 1 plus 1 into 1, 1 into 1 is 1, 1 into 1 is again 1, 1 into 2, and plus 1 into 3, 1 into 2 is 2, and this is 3. So now I write this as it is, 3 minus 2 minus 1 1, this is 1, 1 plus 1 2, 2 plus 0 2, 2 plus 3 5. This is okay, 1 plus 0, 1 plus 1 is 2, 2 and 5, and we multiply these two now. So again we consider first row multiplied by first column, 3 into 1, that is 3, minus 2 into 2, minus 4. Then first row second column, 3 into 2, 6, and minus 2 into 5, that is minus 10. And we repeat this same process for second row. First column, minus 1 into 1, minus 1, 1 into 2, 2, minus 1 into first row into second column, minus 1 into 2 is minus 2, and plus 1 into 5, that is 5. So now we rewrite this. 3 minus 4 is minus 1, 6 minus 10 is minus 4, 2 minus 1 is 1, 5 minus 2 is 3. And here you can observe that this entry is non-zero, therefore this is not an element of subgroup H. For an element of subgroup H, upper right entry must be 0, and we have seen that this element A inverse D into A is not present in subgroup H. So we have obtained particular matrices capital A and H. Okay. Therefore we can write that for A belongs to G and D belongs to H, this is not a member of subgroup. A inverse D into A is not present in the subgroup, and if H is a normal subgroup, this must be true for every element of group G and every element of subgroup H, and we have obtained those matrices capital A and capital D for which this condition is not satisfied. Therefore we can say that H is not a normal subgroup of given group G. H is not a normal subgroup of group G. If you want to prove that H is a normal subgroup, you have to prove this condition: A inverse dA belongs to H for any element of group G and for any element of subgroup H. But if you want to disprove that H is a normal subgroup, then you have to find out particular matrices. You have to show the existence of matrix in group G and existence of matrix in subgroup H such that this condition is not satisfied and these two matrices are working. I have taken this matrix as A, this matrix as D, and I find that A inverse D into A is not present in H, therefore H is not a normal subgroup of group G. So in this way we can decide whether our subgroup is a normal subgroup or not. First you can try to prove, and if you think by intuition that this might not be a normal subgroup, then you can try by taking particular elements in the group and in the subgroup. And if by trial and error, if you find that this condition is satisfied for particular values, then you can try to prove that it is a normal subgroup. So this is all about this session. I hope you can understand now that how to prove that given subgroup is a normal subgroup, or how to disprove that given subgroup is a normal subgroup. So I stop here. Thanks for